Hello, my name is Nobuaki Tanaka from Biotechnology Corporation. We have Hisashi Yomiya and Kiyoshi Ogawa as co-authors. First of all, we would like to thank to the staffs and secretariats of DECSoS and SafeComp who hosted the conference under this difficult situation in the world. We would like to express our gratitude to the reviewers who gave us essential comments to our paper and our activity. First of all, we would like to explain our paper's overview. We think that the objective of our activity is to visualize safety analysis result in a more understandable way to ensure that safety mechanisms mitigate the effect of failures. One solution to achieve the objective is to create a model that integrates safety analysis result with system design and divide the model into diagrams according to reviewers' concerns. As a result of our activity, we confirmed that the method could visualize how the safety mechanisms protect against the effects of a failure on internal block diagram. And we could visualize the result of FMEA MMSR with the proposed method. And one thing we found in the activity that is that in the case study, we could understand that the safety analysis results interact across the boundaries of the system design elements. I will explain these topics in turn. This slide shows the issue and the objective in our activity. My understanding of the situation in embedded system development is that the system is getting more complex and larger. And that kind of huge development requires huge organization. And communication between developers, in particular designers, analysts, and reviewers is becoming more important. We think that one issue is happening in the development. To communicate the result of safety analysis is becoming difficult. In particular, it is difficult to communicate how the safety mechanisms of functional safety mitigates the effect of failures. One reason of the issue is that the increasing complexity and size of products, obviously, but thinking about the functional safety standards such as 26262 and 61508, the standard requires independence of reviewers and developers. Therefore, it is difficult to understand the design and the safety analysis results for reviewers. So we defined our objective of our activity as to facilitate reviewers' understanding of the safety analysis artifacts to solve these issues. We think that MBSA, model-based safety analysis, is a key technology to improve understandability of safety analysis results. We found some definitions of MBSA in various papers. But we think in our paper, we use the term as the abbreviation for the safety analysis using a model-based technology. And let's go on to the next topic, problems. What is the cause of the issues? We think that two issues cause the problem. Excuse me, two problems cause the issue. One is a low cohesion of related information. Reviewers' concerns are dispersed across several documents. That is one problem. The second problem is that lack of graphical expression. We think that relationships between system model and fault model should be visualized, and the sequence of failures, occurrence, detection, system response, and factors should be visualized. This slide explains our intention to use the technical word called low cohesion. We think that information is dispersed across artifacts of safety analysis. Please see the left-hand side of this slide. Information of failure behavior is dispersed across multiple artifacts in system design documents, FMEA sheets, and FTA diagram. Please see the right-hand side of the slide. It should be easier for reviewers to understand the information about the failure if it is represented in one place. We mean, let's aggregate the information which is a concern of the reviewer, the user of the document. On the second problem, graphical representation. If we think about the sequence of the effect of a failure, please see the left-hand side. Fault tree model is suitable for failure rate calculation, and it is necessary, but the model does not express sequence of failures, occurrence, detection, system response, and effect. And the activity model is on the other side. Suitable for representing sequence of failures, behavior, safety mechanisms, and effects as flows. Therefore, in some cases, activity model is beneficial for the users. The second graphical representation is relationship between system model and the fault model. Visualizing the correlation between the system model and the activity model will facilitate the understanding of failures behavior. The activity model is suitable for representing the correlation because the activity model structure is similar to the system design. So if we draw the line that describes the relationship between system design elements and the fault model, it will make it easier to understand the system's behavior when failure occurs. That is our intention to represent the relationship between fault model and the system model. And if activity model is beneficial, how can we get the activity model? We think that two sources are available for constructing activity model. One is a FMEA-MSR. FMEA-MSR was introduced in AIAG VDA FMEA handbook published last year, and it analyzes safety mechanisms of functional safety. Therefore, the result of FMEA-MSR contains information of safety mechanisms, and that we can utilize the information. And the second one is FT diagram. If we make a FT diagram intentionally, in order to investigate the possibility of converting an FT diagram into an activity model, we intentionally created an FT diagram that includes interactions and try to convert and import the FT diagram into internal block diagram. This is a brief explanation about the FMEA-MSR. FMEA-MSR analyzes failure causes and the customer operation conditions, and it contains failure mode. It considers whether or not failure mode cause are detected by the system. As you can see in the right-hand side of the figure, the slide. Therefore, the result of the FMEA-MSR contains the information about the safety mechanism, the monitoring, system response, and mitigated failure effect. Therefore, we can utilize this information to visualize, to construct the activity model, and we can visualize them. And next, This slide shows the solution for the implementation of solutions and how we implemented how we solved the problem, how we provided the solutions. First one is design the notation of fault model. Designing a notation can be, we designed a notation that can display system model and fault model in one diagram. With self-DML, which was presented in the self-comp 2090 last year, and system ML 2.0, which is under standardization. If they are available in our activity, we can use them maybe because we are not familiar with, we are not expert for that, or they are not available in our activity, but they can express the fault model. So, but in our activity, we designed our own notation to utilize the notation for the visualization. Second solution is that we imported fault model to the system model. We imported FTA and FMEA data into system diagram. We developed the prototype functionality in a software tool. Third solution is that we divided the combined model in a system tool according to concerns, divided the model according to concerns. Divide them according to concerns means we think that one big or one important concern in review is the effect of failure, effect of one failure. So we divided the model according to a failure. This slide shows the meta model of the proposed diagram. When designing UML or SysML related diagrams, meta models are used to express the design of diagram, design of the notation. The meta model abstracts the logical structure of elements and the relationship in the diagram. We provided a system model in the figure 2, but we utilize the existing SysML diagram for describing the system model, which is written in a SysML. And the right-hand side, fault model, fault model is not available in a SysML, so we designed, we added failure mode detection, system response, and the failure effect in a fault model. And we also provided a relationship between fault model and the system model. This slide shows how we converted an imported safety analysis result into a SysML diagram. Please, let's go on to the next slide. Right-hand side of the slide, figure 3 in proceeding. Right-hand side of the figure 3 shows the procedure to import elements and relationships described in each safety analysis result. On the other hand, left-hand side of the slide shows the procedure to provide relationships between different safety analysis results from traceability info, because the relationship between different artifacts are expressed in safety traceability information or in other format. For example, the developer provides us same ID to same element in different artifacts to show the relationship between the elements in different artifacts. Relationships between components in different artifacts, we provided the relationship as a separated data format to the prototype tool. And we imported FTA and FMEA result into a system diagram, and we get the model of failure chain with the internal block diagram. This slide shows how we converted fault tree model to activity model. And fault tree model does not express the sequence of the effect of failure. So we embedded the kind of element, the information about the kind of element in FT diagram intentionally. And we defined that the sequence shall be determined by the type of element. So we could construct activity model from the fault tree model. And the right-hand side of the this slide shows the table 1 in a proceeding that shows a correspondence between system design and safety analysis result when we use the internal block diagram in SysML. And that table shows the relations between different artifacts. And the third solution is how we divided the model according to concern. As we explained earlier, we in our use case, a case study, in our case study, we defined that the concern of the user, in this case, reviewers, is failure, the effect of a failure. So we developed a prototype functionality to divide the combined model according to concern, according to one failure mode. And that means if the operator, if the user specifies one failure mode, the the functionality extracts the effect of failures, and the extracted effects are merged into internal block diagram, and the functionality displays the sequence of effect in IBD, internal block diagram, as you can see in figure 7. And this slide shows the example of in our case study. The left-hand side of this slide, figure 7, shows the case we use the FMEA MSR only. That diagram, in our diagram, safety mechanisms and the mitigated effects are visualized in conjunction with system design. You can see, as you can see. And the right-hand side, we added information from a FT diagram, which we intentionally made. And we converted the FT diagram to activity model and merged the information into the system design. And detailed failures behavior imported from FT diagram shows how the failure propagates to the safety mechanisms. But the diagram is a little bit complicated, and it's we think that the reviewer or the user of the tool or functionality should judge which diagram or which notation should be beneficial for the practical use. This slide shows our conclusion. With the proposed method, we could correlate the safety analysis result with the system design and visualize them. The diagrams created from FMEA result facilitate understanding that safety mechanisms mitigate the effect of failures. And we, in the case study, we found that the diagram shows the result of FMEA MSR do not show the effect of failures in detail in one-to-one correspondence with system design components. So there is a difference between the description. And monitoring system response and effect interact across the boundaries of the system design components. We can see we should consider how we should visualize this kind of difference, this kind of heterogeneous model, or this situation. We have not investigated further, but we should investigate how we should visualize this situation. This is our future work. We applied to a case study. We applied our method to a case study, but we should apply this method to larger system or product development. And the second one is we focused on the visualization, and improvement of the understandability of the artifact, but we think we should utilize this technology, including MBSA, to improve the safety analysis work entirely. Third one is the problem we explained in previous slide. Consistency among heterogeneous models, safety model and system model. We found that we can visualize the difference in our proposed diagram, but this is an important topic in MBSA, so we should investigate further. This concludes our presentation. Thanks.